Here we have a pre-built version of the application. So if we go ahead and run it, and I have the weather dataset set as default, and let's run in verbose mode so that we can see all the calculations. And let's generate those rules that allow us to make decisions. And here for this data set, we calculate the information gains, and we find that Outlook has the highest one. So we split on that, and we have Outlook is overcast, and it is rainy, and it is sunny. And if it is overcast, the decision is to play outdoors. So we have this rule, and for Outlook is rainy, we have those two rules. So here we have this data set for Outlook is rainy, and we calculate the information gains, and we find that windy has the highest one, so we split on that. And if windy is true, the decision is to not play outdoors, and if it is false, the decision is to play outdoors. And if Outlook is sunny, we have this data set, and we calculate the information gains and find that humidity has the highest one, so we split on that. And if humidity is normal, the decision is to play outdoors, and if it is high, it is to not play outdoors. So we have those two rules. And let's try making some decisions. So let's see, for Outlook is overcast. So the decision is to play outdoors. And let's try to confuse it. So maybe add windy is true, and it still makes the same decision, so it is only using the first attribute. And let's see if it makes a decision with only this attribute where two are needed, so it cannot do that. And I have two data sets set up in the system. So let's pick up this contact lenses data set. And let's generate the rules for this one. So we have those 9 rules. And since we are running in verbose mode, I am displaying all the calculations. So here we calculate the information gains for the original data set, and we find that the tier prod rate has the highest one. So we split on that, and we have two tier prod rate, either normal or reduced. And if it is reduced, there is no prescription. So we have this rule, and if it is normal, then we calculate the information gains for this data set, and we find that astigmatism has the highest value, so we split on that, etc. And let's quickly do a test run. So maybe pick this one. And before moving forward to the code, those are the equations for entropy and information gain. And the best way to understand those equations is to go over the calculations. So here for the weather dataset, we are calculating the entropy, and then we are calculating the information gains for the four different features. So for outlook and temperature and humidity and windy. And we find that the outlook has the highest information gain, so we decide to split on that. And for the contact lenses dataset, we calculate the entropy and the information gains for age, spectacle prescription, astigmatism, and tear prod rate. And we find that tear prod rate has the highest information gain, so we split on that. I will start by creating a new Python file. Now all nodes in this decision tree will end up extending from this abstract class. So this result node will be a leaf node, and it will extend directly from abstract node. And for simplicity, we will have this composite node class extending directly from abstract node, so we will not have like an abstract composite node in between. Now this abstract class will not have a parent or a name or a value, and those are initialized in the constructor for both result node and composite node. Which contains a list of abstract nodes. And here in the abstract class, we have those get methods for the parent, the name, and the value, and the name value pairs. Returned as name equal value. And we have this set method for the parent. And for the composite node, we have this get methods for the child nodes, and the toString method will return name equal value for this composite node. And same for the result node. And the rule class here will represent a tree branch, so it will have a result node and branch nodes. And we will have get methods for both of those. And this method will return the name value pairs. And the toString method will return the result for this rule. So the tree branch nodes and the result node. And we will be using those two datasets. So the weather dataset and the contact lenses one. And we will have this dictionary containing both of those, so we can add or remove datasets in the future here. And this class will represent a dataset. So in this case, the weather or the contact lenses one, and it will have a name and a data that are initialized in the constructor. And this class will represent a feature in the dataset. So this is a column for that feature, and this is dataset data. And the first row in our datasets contains the heading. And this class will represent a feature value. So this is the name of that value in a feature. And this class will contain the decision tree logic, so it will end up containing a list of rules that are generated. and the feature value will have a number of occurrences within the feature, and get methods for both the name and the number of occurrences, and a set method for the number of occurrences. And this toString method will return the name of this feature value, and I have the equal and hashcode methods, since we will be comparing this feature value against other feature values. And a feature will have also a set of values, and get methods for the name and the values, and the toString method will return the name of this feature. And this code will initialize the feature values for the passed in column, and here we are setting the number of occurrences of each feature value in this feature. And here in the dataset class, first let's go ahead and use text table, since we need to display the dataset in table format. Here in the toString method, and we need get methods for the name and the data. And before moving forward, let's do a quick reminder. So this is the equation for the entropy, for calculating the entropy, and this one is for calculating the information gain. So the entropy of S, which is a collection of C outcomes, is the summation from X is 1 to C of minus Px log base 2 of Px, and Px is the proportion of S belonging to class X. And the information gain is original entropy minus the summation of the number of samples in a split group over the total number of samples multiplied by the entropy after the proposed split. And this method will create a dataset given a feature and a feature value within that feature. And this method will return a column number given a column name. And those three methods will make use of the equations we just went through to calculate the information gains and the entropy. So this one calculate minus p log base 2 of p, and let's go ahead and import log from math. And this one calculates and returns entropy. So it uses minus p log base 2. And here we make use of those two methods. And this method finds the split on feature given the information gains that we calculated here. And we call that method from here. And what remains are get methods for the entropy and the split on feature and the information gains. And this one returns the information gains values. And this method handles prompting the user to choose a dataset from the list of available ones and picking up that dataset and returning it. And this method handles generating the decision rules, and it ends up calling the generate rule method that generates and returns each one of the rules. So we start from the result node and ask it for its parent, and then we get the parent of each one of the parents, and this way we get the branch nodes, and we pass in the branch nodes and the passed in result node in order to create a new rule. And here we put all the created rules in this list of rules. And here we are handling the case where we are not at a leaf node, so the entropy is different than 0. Otherwise, if the entropy is 0, then we are at a leaf node, and this is where we are handling that case. And in this case, this method ends up recursively calling itself here and here. uh, here we are prompting the user to make a decision by entering key value pairs separated with commas, and then we end up calling this method to return the decision. For example, in the case of the weather dataset, the user enter the attributes and their values, and this method will return the decision whether to play outdoors or not to play. So here we are handling the rules generation by calling the generate rules method, and then after doing that we go into an always true loop, making decisions given key value pairs entered by the user. And when the user chooses to exit, we break out of that always true loop. And finally, this function handles command line entry. So here we are prompting the user to choose what they want to do, either generate rules or choose a dataset, or go into default mode, or go into running in verbose mode, or if they want to exit the application. And if we are in verbose mode, we display all the calculations. So here we are handling rule generations, and here we are handling allowing the user to choose between one of the datasets that are available, and we break out from this always true loop if the user chooses to exit. And finally, let's go ahead and test run the application, and let's go ahead and generate decision rules and try to make some decisions. So for outlook is sunny and humidity is high. The decision is to not play outdoors. Let's try if we only have the value for the outlook attribute, and we cannot make a decision in that case. How about if we have outlook is sunny and windy is true? And we also cannot make a decision in that case. How about if outlook is overcast and here the decision is to play outdoors, and let's choose a different dataset from the available ones. So let's pick the contact lenses one and generate the rules for that. So we have 9 different rules for this contact lenses dataset. So let's try this one. don't have a prescription in that case. How about if we try the same one but without the last attribute, and we cannot make a decision in that case. And let's do one last thing, just test run the verbose mode, and maybe go with the weather dataset again. And generate the rules here. So we go through all the calculations. So for the original dataset, we find that Outlook has the highest information gains, and we split on that, etc. And then here for Outlook is sunny, we find that humidity has the highest information gains, and we split on that, etc. And let's do one last test.